Imagine if you were a Go master, having spent decades honing your skills, mastering countless sophisticated tactics. But one day, an AI system that knows nothing about Go strategies surpasses your level simply through repeated play. This is not science fiction, but a reality that has already happened. Today, we want to share an important discovery from Richard Sutton, the 2024 Turing Award winner, the father of reinforcement learning. In the field of AI, human expertise may not be the shortcut to success. Why is this discovery called the bitter lesson referred to as bitter? And why is it so important for the development of AI? This answer might make many experts uncomfortable. In the history of AI development, systems that abandoned the use of human expertise and instead relied on general learning methods often achieved better results. This discovery not only changed the direction of AI development, but also profoundly influenced our understanding of artificial intelligence. Let's take a look together. What kind of wisdom is hidden behind this seemingly counterintuitive discovery? You see, over the past few decades, AI researchers have been pursuing a seemingly reasonable direction, encoding human expertise into AI systems. This idea sounds very reasonable. After all, humans have accumulated a wealth of experience and deep insights in many fields. However, history has repeatedly told us that this path may not be the optimal solution. Let's look at a very interesting example. In the development of computer Go, researchers initially did this. They invited professional players and carefully recorded their thought processes, then turned these strategies into rules that computers could understand. For example, in the opening, occupy the four corners first. When you see your opponent's cutting points, consider whether to reinforce them, and so on. These rules indeed helped computers learn basic Go skills. But even after years of improvement, such Go programs could only reach the level of a strong amateur. Later, AlphaGo adopted a completely different approach. It used deep neural networks combined with a technique called Monte Carlo tree search, learning by continuously playing against itself. To be more specific, AlphaGo first learned to imitate human moves, mastering the basics, and then began playing against itself, continuously improving its level. In this process, it didn't need anyone to teach it specific strategies, relying entirely on its powerful computational capabilities and general learning methods. As you know, it not only defeated top players but also created many eye-catching new moves, such as the famous 37th move, which human players had never thought of before. In the field of speech recognition, we can see a similar situation. How did early speech recognition systems work? Linguists first defined a set of rules. For example, in English, consonants usually cannot appear consecutively more than 3 times. Certain phonemes change under specific conditions, and so on. Engineers wrote these rules into programs, hoping that computers could understand speech like humans. Such systems might perform well in the lab. But once in real-world environments, encountering various accents and background noise, the accuracy rate would drop below 60%. Current speech recognition systems use a method called end-to-end deep learning. They learn directly from audio signals without any predefined linguistic rules by training on a large amount of real-world speech data. These systems can adapt to various accents and environmental noises, achieving an accuracy rate of over 95%. Especially when dealing with heavy accents, rule-based old systems might not understand at all, but deep learning systems can comprehend and transcribe them well. When it comes to autonomous driving, this trend is even more evident. The traditional approach is to write human driver experience into rules. For example, stop at red lights, maintain a safe distance, and so on. However, the real-world road conditions are too complex, and relying solely on simple rules is far from enough. You see, Tesla has chosen a different path. By collecting real driving data from millions of vehicles, AI directly learns how to handle various situations. From the most basic lane keeping to dealing with complex traffic scenarios, such as construction zones or driving under adverse weather conditions, it is all learned this way. Although this field is still evolving, this method has already shown great potential. So why do general learning methods always outperform carefully designed domain-specific solutions? Sutton provides a simple yet profound explanation. Computational power is continuously increasing while human expertise is relatively fixed. When we design specific solutions, we are actually limiting the learning potential of the system, preventing it from fully utilizing increasingly powerful computational resources. This This lesson is called bitter because it is indeed a bit of a blow. Think about it. As domain experts, we all feel that our knowledge and experience are valuable and should be taught to AI. But the facts tell us that letting AI learn from data on its own often yields better results. Of course, this viewpoint has also sparked considerable controversy. Researchers who support symbolic AI believe that purely data-driven methods lack interpretability and may pose safety risk in some critical applications. They suggest that human domain knowledge should be combined with machine learning to create hybrid systems. These concerns are indeed valid, but from a historical trend perspective, as computational power increases, purely data-driven methods may ultimately surpass hybrid methods in performance. What insights does this lesson provide for the future development of AI? First, it reminds us to maintain an open mindset and not to rely too much on existing domain knowledge. Second, it tells us that meta learning is important, meaning that rather than designing specific solutions, it's better to develop general systems capable of autonomous learning. For researchers and engineers, this may mean adjusting the direction of work, spending less time designing domain-specific solutions, and focusing more on how to improve the learning algorithms themselves, and how to better utilize the ever-growing computational resources. Of course, this does not mean that human expertise is completely useless, but rather reminds us to use this knowledge more wisely. Looking ahead, computing power is likely to continue growing rapidly. This means the advantages of general learning methods may further expand. However, at the same time, we also need to seriously consider how to address the challenges brought by such methods, especially in terms of interpretability, safety, and ethics. Finally, this bitter lesson may signify a deeper shift in the development of AI, from attempting to replicate human thought processes to allowing AI to forge its own learning paths. This shift might bring more surprising discoveries and deepen our understanding of intelligence itself. Thank you all for watching. If you found it helpful, please like and subscribe. See you next time.